Marginal zone theory and the Fahraeus linguistic effect. So let's look at how the blood flow looks like in a vessel, blood vessel, and specifically how red blood exists, where they exist. So this is the center line of a cylindrical pipe. So usually red blood cells would concentrated around the center region of the vessel instead of everywhere. That is because the hydrodynamic and the cell interaction. So you would have cells mostly existed along the center region. So these are red blood cells. I'm not going to continue to draw, but you get the idea. So if we also, this is the radius R, then you can see there is a region we call this delta. Thickness is delta. And then you know this distance is R minus delta. So for the R position between 0 and R minus delta, it is a region where red blood cells exist. This is called, we call the core region. And you also have a region where you don't have red blood cells. This is called the plasma layer. So at the core region, the effective viscosity, let's call it mu4. And in the plasma layer, let's call it mu plasma. So you can see that the viscosity it should be larger than the viscosity where there is no red blood cells. And when we say mu core, we know that if you have a blood, it's a non-Newtonian flow. Here we mean it's at the high flow rate limit so that the flow can be approximated as a Newtonian fluid. So that's why we have a viscosity for the core region. So now you have, like if you look at the entire blood vessel, you have two regions. One is with cells, another is without the cells. And you can think about what's the overall viscosity of the entire fluid combining the two layers. That's what we are going to derive today. And this we call mu apparent for the entire region. So the entire vessel. Entire blood vessel. The effective viscosity is mu apparent. And then we are going to find this mu apparent. So this is the effective viscosity of the entire region. And what is the Fahraeus linguistic effect? It says that as the blood vessel decreases in diameter, then the apparent viscosity actually decreases. So let me write it down. What's the the Fahraeus Lindqvist effect. It says the apparent viscosity blood decreases as vessel diameter decreases. Up to a critical range of approximately 4 to 7 micron to 500 micron. So that means you cannot decrease the vessel size like infinitely small. You cannot like going down to like 3 micron or 2 micron, 1 micron, and you still expect the effective viscosity decrease. That's not going to happen. So so the Fahraeus linguistic effect works between like 5 micron to 500 micron. That's the range we are talking about. So for the rest of this lecture, we will derive the apparent viscosity by using the marginal zone theory. This is a pretty nice mathematical framework because it tells a lot about how to set up continuity conditions for fluid of 2 layers. So what we are going to do is exactly as I said, we have 2 phases of fluid. One phase is the core region. This is the core. Another is the plasma region. And we will model these 2 layers separately. So each layer would have its own equation. And then we will have boundary conditions that combine the 2 layers together. And then we will use boundary conditions to solve the governing equations. And then we will get their velocity and the volumetric flow rate of the entire vessel. Now let's look at the core region. So let's do one by one. So in both the core region and the plasma region, we are saying it's at the Newtonian flow limit. So the core region is, as we said, it's valid between 0 and minus delta. So for this region, let's look at the shear stress. Shear stress, let's say tau over the core region. So we know that for a force balance, the stress for any type of fluid, it should equal to minus R divided by 2L delta P. This is from force balance. And on the other hand, we know that since we approximate as a Newtonian fluid, this should equal to the viscosity of the core region multiplied by the shear rate, dV core. V core is the velocity profile within the core, dr. So this is the governing equations. Let me write it. Let's see. The thing is, it works from time to time, it stops working from time to time. So, or equals minus R 2L delta P equals to L or B Z or R. So this VZ or is the velocity profile within the core region, as a function of R. So we have B dV dr. And the boundary condition for the core region, we have two boundary conditions. BC1 is at the center line. We know that there is no shear stress, or the profile is symmetric. Symmetric means dVz core dr equal to 0. If you recall the parabolic profile for the Newtonian fluid, the Poisson fluid, the derivative is 0 at the center line. And this boundary condition 2 is at R equals to R minus delta, this is at the interface of the core and the plasma. The tau, the shear stress of the core part should be the same as the shear stress of the plasma. Although we don't have an equation for plasma yet, but we know this is the boundary condition. So this is a condition we call the continuity of shear stress. Across the boundary. Across the boundary of two fluids. Or two faces of fluid, maybe so two faces of fluids. Two faces means a core region versus a plasma region. Now let's do the same thing for the plasma layer. This is from R minus delta to capital R. And then we can still find the shear stress. So although this can be a little bit, you may find it intimidating to think about a plasma layer because it's now not at the center. It's not close to the wall, then what's the shear stress? Now, regardless of how the fluid organized within the vessel, as long as it's a fluid, then the force balance equation tells us how plasma is equal to minus R 2L delta P. So this shear stress, again, it is always true as long as you have a cylindrical pipe. It has nothing to do with the constitutive relation of the fluid. And then now for the plasma, we still apply Newton's law because we also assume it's a Newtonian fluid. So you have a mu plasma dV plasma, ER. So the plasma is the velocity of the fluid in the plasma layer. It's also a function of R. So we are going to find this, going to solve for this. Same for the core, we are going to solve for it. Now let's look at the boundary condition for the plasma layer. So we have boundary condition 1 and 2 for the core region. Let's continue to write the boundary condition 3. Because this is the entire problem, we can treat it as 2 equations and 4 boundary conditions. So at R equals to R minus delta, it's at the interface. Then we have continuity conditions of the velocity, Vz or equal to Vz plasma. This is a continuity of fluid velocity across the boundary of 2 phases of fluid. Now let's look at the fourth boundary condition. This is at R equal to capital R and Vz plasma is 0. This is no slip boundary condition. Okay, we have 2 equations for boundary conditions. The 2 equations means this is 1 equation. This is the second equation. And we have 4 boundary conditions. Now to solve this, let's first solve the plasma layer. It is relatively easy to handle is because we know that the 0 boundary condition, like the non-zero boundary condition, is enforced at the wall. And you may wonder, what about the boundary condition 1 and 2? Actually, if you look at the 2 equations, you will see that the boundary conditions 1 and 2 are automatically satisfied. So this is important to note. BC1 and BC2 are automatically satisfied. You can just based on the 2 governing equations. I suggest you verify this on your own. This is important to recognize this, and it's a good exercise for you to have some practice of how to look at the equations and the boundary conditions. So basically, you don't need boundary condition 1 and the boundary condition 2 as long as you follow these 2 equations in the boxes. So let's first solve the solve for let's solve for the velocity profile. Now let's do the plasma layer. For the plasma layer, if you look at the equation in the box, you can just directly integrate. So integrate, what I mean is you can write dV the plasma equal to minus R delta P 2 mu plasma L dr. And then you use the, once you integrate once, you will get a constant of integration, and then use the non-slip boundary condition. You will get to this BZ plasma. I strongly suggest you work out this on your own, because we solved this before. So it's like a review, and make sure that you know how this is solved. So I'm going to solve this for you, but you verify it on your own. It's delta PR squared divided by 4 mu plasma L multiplied by 1 minus little r divided by capital R squared. And then you can integrate to find the volumetric flow rate within the plasma layer. So if you want to find the Q plasma, what you need to do is you integrate from, instead of from 0 to R, you integrate from R minus delta to capital R, because this is the region where the plasma exists. And then you have your element of integration is 2 pi R multiplied by VC plasma as a function of R, integrated over the R. And again, check on your own, you will get pi R to the power of 4 delta T divided by 8 mu plasma L. And so we have solved the velocity profile and the volumetric flow rate along the plasma layer. Now let's find that in the core region. So we also integrate the equation for the core. So we are going to integrate dVz core equal to minus R delta P 2 mu O L dr. And in this case, so in the previous case, we used boundary condition 4. And then we will get the velocity. Now here we use boundary condition 3. And then we will get the velocity in the plasma layer. Sorry, in the core region. So B, C, 4 as a function of R. It's a little bit long in terms of the expression. It looks intimidating. It's just because the algebra is more involved, but the physics is there remain the same. So it's delta PR squared divided by 4 mu plasma multiplied by L. So this is 4. Then you have a big parenthesis. So verify this on your own. It's important to be able to verify these as a practice. It's not hard, you just need to be patient. So take out a piece of paper and a pen, just work out this turn by turn, and you will get that. This practice also helps you to just review a little bit of doing integration and manipulating the algebra terms. Okay, this is the expression. And if you want to find the Q for the core region, what you are going to do is now you integrate from 0 to R minus delta, because this is where the core exists. So if you do the calculation, you will find it as another expression. I R to the power of force delta P divided by H mu plasma L. Then we have a big term, big parentheses. And you can also derive this as long as you are patient. So this is the volumetric flow rate over the core. And now if you are asking, okay, now we have the volumetric flow rate across each region, then what is the total volumetric flow rate across the entire cross-sectional area of the vessel? That is what we needed to find, because that's what we are going to solve for the effective or apparent viscosity. The Q, total Q, is Q plasma plus Q core. So you just add up these two together, and again, you just need some patience. It's not hard, you just work out. So try to verify it on your own. You will get this I R to the power of force delta P divided by H mu plasma multiplied by L. Then in the parentheses, after you combine the two terms and then you do some cleanup, it becomes something a little bit short. So that's good. Okay, that's it. Now, how does that tell us the effective viscosity of the pipe? Let's recall the Newtonian fluid for the Pasolini equation. Recall the Pasolini equation. For a Newtonian fluid. So we have Q equals to I R the power of force 8 mu L delta P. If you compare these two, so you compare. You can see that for the blood vessel, when you have a core region and a plasma region, you get something, you have a correction term. So the coefficient in front of the square parentheses brackets, they are almost the same. You just have mu, regular mu replaced by mu plasma, and then in the plasma case, you have another correction term. So that means the apparent viscosity or the effective viscosity of the entire blood, mu apparent, is a correction on the viscosity of the plasma. One minus parenthesis 1 minus delta divided by r to the power of 4th multiplied by 1 minus mu plasma divided by mu 4. This is the apparent viscosity we want to find at the beginning of this lecture. So this is it. As you can see, we have some special limits as delta divided by r go to 0. That means the plasma layer shrinks to 0 and the entire region becomes the core region. You can look at this apparent viscosity. You know that the mu apparent approaches the core viscosity. On the other hand, if delta divided by r approaches to 1, that means the entire region is almost dominated by the plasma layer. There's almost no core region. And no surprising, if you look at this apparent viscosity, you get mu apparent approach to mu plasma. So you can verify this. So you can just let this delta divided by r either take the value of 0 or take the value of 1, and you get two limits. So this is one way of doing like sanity check if the apparent viscosity you obtained makes sense or not. Sometimes if you make some like simple mistakes during the derivation, and then you may arrive an expression for apparent viscosity, which may not be correct. So two things you should always check. First is check the dimension. Does the dimension of every term make sense? Then the second thing to check is to check the physical reality. Does your expression make sense at some limits of some physical processes? If both of these checks make sense, then although you cannot guarantee your expression is correct, but at least you can say, okay, I don't find anything obviously wrong. Then you are confident about what you derived. Otherwise, if you derive something that you can check that dimensionally it's not correct, then for sure you have done something wrong in the process of derivation, and then you should go back. So these are all the sanity checks that you should do. Okay, now we have the apparent viscosity, and what can we do with it? Like for industrial application or biomedical application, what do we do? Or like how do we measure the apparent viscosity, or how do we measure the core viscosity and the delta if we have something? So the apparent viscosity usually you can measure through a viscometer. Like as we discussed earlier, you find some way to identify its apparent viscosity of the entire flow. And then you are going to use this equation to figure out what is delta what is mu core, provided that you know what is mu plasma. So let's see how people do that. Here we have analytical approximation and data fitting. So usually for delta divided by R to be much less than 1, it's usually the case. Then we know from calculus 1 minus delta over R to the power of 4. This is approximately equal to 1 minus 4 delta divided by R. So if you forget why this is approximately true, you can just do a Taylor expansion and you will get this. This is the first, you return the first order term in your Taylor expansion. So now you can rewrite your apparent viscosity by using this term. So mu apparent equal to mu plasma divided by 1 minus 4 divided by R and multiplied by 1 minus mu plasma. And then you can do some algebraic operation. I'm just give you one more step, and then you know what's going on. It's not something magical. Again, you just need a patient. It's not hard, but just spend some time to work on it. You will get it. You like multiply these two terms. 1 minus mu plasma mu core minus 4 delta divided by R plus 4 delta mu plasma divided by R mu 4. Okay, now you can continue to clean it up, and then you can just try on your own. And eventually, you will get this, and then you flip both sides. You flip the right hand and the left hand side. You get 1 over mu apparent equal to 1 over mu core plus 4 delta mu core multiplied by mu core divided by mu plasma minus 1 multiplied by 1 over R. Now you look at this. This is, you treat it as like a plot of, if you do experiment and plot this, a plot of 1 over mu apparent versus 1 over R is linear. And to get this, you will do experiment for several different R values. So you can change your change your vessel diameter a little bit. You get different capital R, and then you do measurement, you get a different mu apparent. Then you would plot 1 over mu apparent versus 1 over R, and then you fit it as a line. It will give you a linear. So if you plot 1 over mu apparent versus 1 over R, it a linear line. Linear fit. Then you get a slope, and then you get a y-intercept. The y-intercept is 1 over mu core. The slope is the coefficient in front of the 1 over r. And you will get immediately get the y-intercept after you fit the linear line, and then you can solve for mu core. Once you solve for mu core, you plug in into the slope because you also know the slope after fitting. Then you can solve for delta. So from these two, you are able to find mu core and the delta. Assume we know mu plasma already. So that's how this equation is used in reality. Okay, that's what we would like to cover. This is the marginal zone theory. Now let's leave 1 or 2 exercises for you. Exercise 1, discuss the effect of decreasing R on apparent viscosity on the marginal zone theory. Basically explain how the equation we just obtained can be used to explain the Fahraeus Lindqvist effect. So, and also, discuss the effect of decreasing on apparent viscosity, and also discuss its physiological significance. Okay, maybe that's it. Let's just leave 1 exercise and not 2. All right, that's all for today. In case you cannot read in case you cannot read my handwriting, let me read this exercise again. Discuss the effect of decreasing R on apparent viscosity from the marginal zone theory and its physiological significance.